So now we are going to talk about the chapter 20, Permutations. We are doing a book, a concise introduction to pure mathematics. So by Martin Lebec. So let's start. To define the permutations, we create a set. Now, by a permutation of set, we mean a bijection from S to S. Okay. That is a function from S to S that is both onto and 1 to. So you can say permutations are the pleasant and useful class of functions, and we describe them in the example as follows. So we consider a set which has elements 1, 2, 3, 4, and 5, and we say that let f, g are two functions from S to S, and they are defined as follows: that f sends 1 to 2, 2 to 4, 3 to 3, 4 to 5, and 5 to 1. Okay. G sends 1 to 3, 2 to 4, 3 to 1, 4 to 2, and 5 to 4. And then we say, then f is a permutation of S, but G is not. And if you want to ask the reason is 2 is also going to 4 and 5 is also going to 4. Okay. Number 2. So this is number 1. Number 2 is we have a function from function f from R to R, real numbers to real numbers, given by that f of x is 8 minus 2x for all x in R is a permutation of R, because in the previous chapter Example 19.32, we have said that this function is the bijective function. Okay. Now, frequently, we consider permutation of sets. We consider permutations of the set which has 1 to n elements. We denote by Sn, which is the set of all permutations of the set of n elements. Now, for a permutation f inside Sn, we use the notation for a permutation f inside the Sn. We use the notation that is that we have 1, 2 up to n, and then we have f of 1, f of 2 up to f of n to describe f. This notation completely satisfies what f is, and it gives the value of f of I for every I inside the set 1 to n. So, for example, for example, 20. So this has a name which is 20 point, example 20.1.1. Number 1, we could say that the permutation f of the set 1, 2, 3, 4, 5 is 1, 2, 3, 4, 5. Remember, 1 goes to 2, 2 goes to 4, 3 goes to 3, 4 goes to 5, and 5 goes to 1. So, like that. Okay. This is how we use this notation. Now, then we have a proposition which says that (20.1) the number of permutations in Sn is n factorial. And we can prove this theorem by using the multiplication principle and proposition 16.1. So we say that if f is a permutation in Sn, then the sequence f of 1 to f of n is just an arrangement of the numbers numbers 1 to n in some order. Hence, the number of permutations in Sn Sn is equal to the number of such arrangements which is n factorial by proposition 16.1 defined before in chapter 16. And this will prove the theorem, the proposition. And we can talk about that by given an example, and we call it 20.2. We say that there are 3 factorial, which is 6 permutations in S3. Okay, and to show them, we have I, which is doing nothing, just fixing everything. So we call it identity permutation. Then we have, let's say, F2, which is fixing 1 and sending 2 to 3 and 3 to 2. Then we have F3, which is sending 1 to 2, 1 to 3, 2 is fixed, and 3 is 1, 3 goes to 1. Then we have F4, which is sending 1 to 2, 2 to 1, and 3 is fixed. And then we have F5, which is sending 1 to 2, 2 to 3, and 3 to 1. And F6, which is sending 1 to 3, 2 to 1, and 3 to 2. Okay, so these are 6 permutations in S3. Now notice that I is the function that sends everything to itself. We call the identity function. Now for any state S, the identity function is a permutation of S, which we call the identity permutation. Okay, perfect. Now let's talk about the composition of permutations. Okay, now let's say if F and G are permutations of a set S, the composition F compose G is defined as in the previous chapter by F compose G of S is F of G of S for all S in S, right? By proposition 19.2 part 2, F of G is also a permutation because it is bijective of S. So in dealing with permutations, we usually drop the small composition symbol. We just write FG instead of F of G. So let's explain it more by the example. So example 20.3. So let's say if F2 comma F3 are in S3, then F2 F3 sends 1 to 2, 2 to 3, 3 to 1. Remember, F2 F3 means that first do F3, then do F2. And so you can say F2 F3 is 1, 2, 3, 2, 3, 1. Okay. How we get this? That means we get. So let's break it out. Let's break it out even more. So we are saying F2 is a function which was sending 1 to 1, 2 to 3, and 3 to 2. F3 was a function which was sending 1 to 3, 2 to 2, and 3 to 1, right? So now you want to do F2, F compose F3, let's say F1, and that will be that you are doing F2, F3 of 1, and that is F3 of 1 is 3. So you are doing F2 of 3, and that is what? F3 goes to 2. So that's why you are sending 1 to 2. Okay. Similarly, F2 compose F3 of 2, and that is F2 F of 3, F3 of 2, and F3 sends 2 to 2. So F2 of 2 is 3. So that's why you are sending 2 to 3. And similarly, that's why you are sending 3 to 1. So this is how this computation shows this. And if you look further deep, you will find out that F2 compose F3 is nothing but F5. Right? Perfect. We can similarly say and send, like compose F3, F2, and that will be the permutation, which sends 1 to 3, 2 to 1, and 3 to 2, and this will be equals to F6. So that means F2 compose F3 is not equal to F3 compose F2. So in order which we formed, the composition of permutations is very important, right? They are not similar anymore in this thing. So using this composition, let's try to compose everything in the S3, and we can do that. So this is part 1 of example 20.3 part 1. Let's do the part 2. So in part 2, we say multiply, or the better word would be compose every permutation in S3 with every other and itself. And to do the better way to do that is writing a table. Writing a table, and that table is going to be that we have identity, we have F2, we have F3, you have F4, you have F5, you have F6. And similarly, we can write identity, F2, F3, F4, F5, F6. Right? And you compose I with I, then you will get I. Compose I with every other person, every other composition, you will get the similar permutation. So this first row is similar. Similarly, if you compose anything with I, you will again get same. Perfect. Now, if you compose something with itself, like F2 with F2, that is I again. Okay. But if you compose F2 with F3, you know that was F5. Similarly, if you compose F3 with F2, you know that was F6. Right? And now I'm going to leave all these parts as an exercise to think about and find out what they will be. They will look like. Okay. So this means we are saying multiplying in composition in permutations is quite similar. Okay. Now, composition also allows us to define powers of permutations in a natural way, because in permutations, composition is multiplication. So you can say that if f is a permutation of a set, so we denote f square to be the permutation which we just did here with this thing. Sorry. So you're composing these two. That means you are doing f compose f is nothing but f squared. So f, let's say f2, f2, right? So let me write that more properly. Okay. So we are saying composition also allow us to define powers of permutations. Permutations in a natural way. So if f is a permutation inside Sn, and define f square is f into f, which is nothing but f compose f, right? Similarly, the f3 is going to be f square compose f, f4 is going to be, so f power 3 is going to be f square into f, f4 is going to be f cube into f, and so on, right? So for example, if I have f as a permutation, which is 1 goes to 2, 2 goes to 4, 3 is fixed, 4 goes to 5, 5 goes to 1, then f, sorry, f square is going to be what? 1 goes to 4, 2 goes to 5, 3 is fixed, 4 goes to 1, and 5 goes to 2. It is not similar to f. And also, f cube is going to be 1, 2, 3, 4, 5, and 1 goes to 5, 2 goes to 1, 3 is fixed, 4 is 2, and 5 goes to 4. You can see those which are fixed, we can't do anything about them, even you square them or like give them any power. Now we need to talk about the inverse of a permutation, so let's do that. The inverse of a permutation f of a set S is also a function, bijective function, which is f inverse, is f inverse, sending everything back to where it came from. So F inverse is also a permutation, and you can write F into F inverse is F inverse into F, and that is I, where I is an identity permutation of S. Okay. For example, let's say F is inside S5, a permutation, which is that F can be written as 1, 2, 3, 4, 5. 3 is fixed, 2 goes to 4, 1 goes to 2, 4 goes to 5, and 5 goes to 1. Then F inverse is going to be 1 goes to 5, 2 goes to 1, 3 is fixed, 4 goes to 2, and 5 goes to 4. If you check, if you send 1 to 2, 2 is sending to 1. 2 is an inverse permutation, 2 is going to 1. If you send 2 to 4, 4 is sending to 2, send to 2, 3 is fixed already. If you send 4 to 5, 5 is sent to 4. And if you send 5 to 1, 1 is sent to 5. So that's how a inverse permutation works. Okay, perfect. Now, there are 4 properties of composition of permutations that are of basic importance, and we list them in the next result. Actually, we have already seen some of these properties, but they are worth highlighting anyway. So let's talk about those results in the proposition. .2. Okay. The following properties are true for the set Sn of all the permutations of the set. So we are saying the following properties are true for the set Sn of all permutations of the set 1, 2, up to n. First property is if f and g are in Sn, so is their product or composition. Second property is for any f, g, h in Sn, the compositions f, g, h is nothing but f, g, h, which means it's associative. The composition of permutations is associative to is done. 3. The identity permutation I in Sn satisfies that F compose I is I compose F is again F for any F inside Sn. And number 4, every permutation F in Sn has an inverse F inverse in Sn such that F into F inverse is F inverse into F is identity. Now, if we would be in the different universe of the pure mathematics, we would list this proposition as a definition and we call it that the set of permutations Sn is a group with the composition operation. Now we are doing an introductory course of the pure mathematics. So we have no language and right to say that to define the groups over here. So that's why we will not, but just to inform that these 4 conditions are there for any set with an operation to define itself a group. Okay. Now we wish to prove them. So let's prove, give the proof. Proof. So we have already seen properties 1 and 4 and 3 is easy. In previous examples, we have already seen properties 1 and 4 and 3 is easy since we say that F compose I of any S is nothing but F of I of S as F of S, which is true for all S in S. Hence, F compose I is F. And similarly, I compose F is again F. So 3 is done and dusted. Property 2 is a little more subtle, but only a little. Let's say 2 for S in S, we have F compose G compose H over S, and that is F of GH S, and you can write that as F G of H of S, while F compose G H of S is going to be f g h of s, and that is going to be f g h of s. So in other words, both this one and this one are are functions, and this proves the theorem, the proposition. Okay, and we would like to end this part of the lecture here. We will try to discuss more about them in the next one. Thank you.